one of the chapters you will learn is waves. When we talk about waves, the first thing that might come to your mind is this thing, something that looks like this. When we talk about waves, the first thing that comes to mind is something that looks like this, right? This one is the image that first comes to mind. And then when you look at an actual wave, the wave normally doesn't remain static. It does move, all right? When I say a wave moves, it looks something like this. Let me share with you a screen. Wait, let me play the animation. Okay, so open. Okay, now on your screen right now, you should be able to see an animation that is playing. So one example of a wave could be something like this too. All right, so you see it has that characteristic wave shape here, but then at the same time, it seems to be moving. All right, so this type of wave is what we know as a progressive wave. Okay, so in the notes, we define progressive wave as a kind of wave where the wave profile moves and energy is transferred from one point to another. When we say wave profile is this shape. Okay, this shape that I actually highlighted before is what we call the wave profile. Okay, this is what we call the wave profile. If you look at the video when it plays, you notice that this particular wave profile, the ones that I've highlighted in pink here, is actually moving from one end to another. It's actually moving from here to here. So maybe this one here is when time t is equals to 0. But then maybe after that, if I let time run, you will notice that maybe at t equals to 2, or say t equals to 1 second, the wave profile is now here. Okay, so as time runs, that wave profile is moving from one end to another end. So this one is what we define as a progressive wave. This is the first wave that you will learn in your AS syllabus. Okay, then when you are talking about progressive waves, what we will tell you is that as the particles oscillate, wait, now let me go back to the original notes. All right, so when the waves is actually moving, wave profile is moving from one end to another end, what's actually happening is that the wave particles are only oscillating about their equilibrium position, but they themselves are not transferred from one point to another along the direction of wave travel. Okay, so one important thing to know about waves is that there is no transfer of matter. Okay, there's no transfer of matter from one end to another. Okay, the wave profile is moving from one end to another, but the particles themselves are actually not moving from one end to another. They are only oscillating about their equilibrium position. So what I mean by that is that if I look back at the original diagram, sorry, original animation, let's just say right now, each square here represents a particle. Right, each of these squares here represent a particle. So say I label them particle A, B, C, D, and E. So if I let the animation run, I notice that the wave profile is moving from one end to another, but the particles that make up the wave, they're actually not moving along from left to right with the wave profile. What they're actually doing is that they're only oscillating about their equilibrium position, up and down. Okay, so since they're only oscillating up and down or about the equilibrium position, they are not being transferred from one end to another. They're still there as the wave travels. Okay, and then one thing that you will need to know is that when those particles oscillate, there will be certain positions where your speed is maximum, certain positions where your speed is minimum. If you look back at the notes, the notes there mentioned that oscillating particles tend to have the highest speed at equilibrium position and zero speed at the amplitude position, because they will need to stop temporarily before changing directions. So what do I mean by that is this. Let's just clear off some of the stuff here. If I refer back to the particles A, B, C, D, and E, where I expect to have maximum speed of the oscillating particles would be here. This is where my V is max, okay? Either up or down, okay? So if I just single out one particular particle, the particle A here, you can see that it will just go up and down, up and down, up and down. So when it goes up and down, at the equilibrium, the speed will be max, but it can be in two different directions. Either it's going with maximum speed upwards or maximum speed downwards, depending on how the wave is at that point. And then another thing here to know is that once your particles oscillate to the amplitude position, your speed will be zero. It's at these positions here, when you reach amplitude position, that your velocity is zero, okay? So once you reach the amplitude position, you go up and then you want to go back down. So that point there where you want to change directions from going up to going down, you will actually have to stop momentarily before changing directions. So at that point where you have to stop momentarily before changing directions, that is usually where your velocity needs to be zero, okay? So when it comes to wave, just remember this, whenever they ask you about the speed of the oscillating particles, it's always the same. At equilibrium, the velocity is max. At amplitude, the velocity is zero, okay? So that one is okay. Then after that, we move back to the notes. Okay, so if I move back to the notes, now for progressive waves, there are actually two types of progressive waves that you will need to know. The first one is called transverse wave. Okay, so transverse wave is where the direction of oscillation of the particles is always perpendicular to the direction of wave travel or energy propagation. Direction of wave travel is always the direction of energy travel also. Okay, it's also the direction of energy propagation. Okay, where the wave goes to, that's where the energy will be going to. All right, so sometimes you will see that they say perpendicular to wave travel or perpendicular to energy transfer, perpendicular to energy travel, energy propagation. They're actually one of the same thing. Where the wave will go to, that's where the energy will go to too. Okay, so transverse wave, oscillation of particles is always perpendicular to the direction of wave travel. So if say, for example, right now I give you an animation of a transverse wave, it actually is this one, the same animation that I was showing you just now. This one is an example of a transverse progressive wave. So if I have a set of particles here, A, B, C, D, and E, they are actually oscillating up and down only. Okay, so this is the direction of oscillation. But what is the direction of wave travel or direction of energy propagation? This is the wave direction or energy direction, if you would. So notice that since my energy direction is here, but my direction of oscillation of particles is up and down, they are actually perpendicular to each other. So this is an example of a transverse wave. Okay, so what is written on the notes there, they say that particles of a slinky spring will vibrate up and down perpendicular to the direction of wave travel. Energy is transferred from left to right without any transfer of spring particles. This one is something which I mentioned just now. Particles oscillating will not move along with the wave. They only oscillate about their equilibrium position. And then one special thing about transverse wave is this. Transverse waves such as electromagnetic waves do not require a medium to travel, whereas other transverse waves like mechanical waves such as a spring, such as a spring vibration or water waves, they all require a medium. Okay, so transverse wave does not necessarily need a medium. There are some examples that need a medium, such as EM wave. There are some examples that do not need a medium, such as EM wave. There are some examples that need a medium, such as spring vibration or water waves. Okay, so this is transverse wave. And then you have the second type of wave, which is longitudinal wave. Longitudinal wave is where the direction of oscillation of particles is parallel to the direction of wave travel or energy propagation. Okay, so how you visualize a longitudinal wave, it looks something like this. I need to share with you a separate screen. Okay, so right now you should be able to see some sort of GIF that is playing on the screen. It shows you a comparison between transverse wave and longitudinal wave. All right. So the transverse wave just now we covered, it is this one. You notice that the direction of wave travel is, wave direction is this, but then the direction of oscillation of particles is up and down. This is direction of oscillation. They are always perpendicular. All right. So this is what transverse wave is. But when you're talking about longitudinal wave, your wave travel is still, say, going towards the right. This is your wave direction. Okay, this is your wave direction. Sorry, let me write it out properly. This is your wave direction. The particles will actually oscillate left and right now. Okay, so it's oscillating left and right. So when you look at the direction of oscillation of the particles with respect to the wave direction, you will see that they're actually parallel to the wave travel, whereas this one is actually perpendicular to wave travel. So longitudinal wave is when the oscillation of particles is parallel to the direction of your wave travel. Okay, so that one is all right. Okay, so again, same thing as before, energy is traveling from left to right, but the spring itself, or rather the spring particles itself, is actually not moving from left to right. They are not transferred along with the wave. They're only oscillating about their equilibrium position. Now, longitudinal waves would be waves such as sound waves or seismic waves. Seismic wave is the waves that is generated when there's an earthquake. All right. So longitudinal waves must require a medium to travel. There are no such thing as longitudinal waves that don't need a medium to travel. Okay, so this is a bit different than transverse wave. Transverse wave does not necessarily need a medium, but longitudinal wave must have a medium. If you don't have a medium, it cannot travel. Okay, so this is one of the main difference between longitudinal and transverse. Okay, so now that you know how a progressive wave looks like in terms of it being transverse and longitudinal, you want to represent the wave in the form of graphs. So when we want to represent the waves in the form of graphs, we would use a displacement time graph or a displacement distance graph. All right. So the displacement time and displacement distance graph will look something like what you see below here. All right. Now for transverse and longitudinal wave, the displacement time and displacement distance graph are actually identical. All right. They will all look like this, a sinusoidal graph with the curves like this. All right. You cannot distinguish between a longitudinal wave and transverse wave just by looking at the displacement time or displacement distance graph, because they all have the same shape. All right. So when you want to plot a graph of displacement time, what we will tell you is that you are plotting the displacement of a single particle in the wave with respect to time. Okay, it describes the same point on the wave but at different time frames, like in a video. Okay, what do I mean by that is this. If I refer back to that little animation, this one here, say this is your transverse progressive wave. If I wanted to plot a graph of displacement time, wait, now let me erase this one. If I wanted to plot a graph of displacement time, what we usually do is that we pick any single point on the wave. So just now I mentioned to you that this wave here could have particles originally at the equilibrium position like this. And then when the wave travels through, each of these particles, A, B, C, D, E, and F, will just vibrate up and down. So this one will go up and down. C, D, E, and F will go up and down. Okay. So when you want to plot a displacement time graph to give you this shape here like this, what you do is that you're picking any one of these points. All right, you pick any one of these points, any one of these particles. Let's just say right now I pick particle A. What I want to do now is that I want to plot the displacement of this particle with respect to time. That will give me this. I could also pick particle B. It will also give me this. C, D, E, or F will all give me the same shape. All right. That's why here in the notes, we say that when you want to plot a displacement time graph, you're actually just picking a single particle on the wave and plotting its displacement with respect to time. Okay, so displacement here is this one here, displacement from equilibrium position. You would have done kinematics already, so your teacher probably would have mentioned it's actually just the distance from a reference point in a specific direction. So in your case, since this one is my equilibrium position, how the particle displaces with time would be my displacement. How far my particle is from the equilibrium is my displacement. Okay, so this is how you will produce a displacement time graph. In the notes, we also mentioned that you could also represent the wave motion using a displacement distance graph. Okay, so be mindful of the wordings that they use. You could also represent the wave motion using a displacement distance graph. Okay, now when you want to produce a displacement distance graph, it is made by plotting the displacement of a number of particles over a given distance at a particular instance of time. All right, it describes different points but in the same time frame, something like a freeze photo. Okay, what do we mean by that? You just refer back to that little animation again. So same thing as before. If I just freeze the diagram first, all right, so let me just plot out the points. Particle A, B, C, D, E. For the sake of simplicity, I'll just make the particles bigger. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's just say particles A, B, C, D, E, F, G, H, I. Okay. So let's just say right now, these were all the particles before a wave traveled through. They were all at the equilibrium position. But once a wave travels through them, each of these particles is being displaced. So A will go up to this point, B will go up to this point, C goes up, D doesn't go anywhere, E goes down, F goes down even more, G goes down also, but not as much, and you have these displacements here. All right. So when you want to plot a displacement distance graph, which could be something like this also, what you're doing here is that you're actually taking into account a number of particles over a certain distance. Okay, when we say the distance, it is referring to something like this. All right. So when you want to plot a displacement distance graph, you're actually considering the wave over a certain distance, and you're plotting the displacement of all the particles within that given distance. All right. So say right now, this is the given distance from here to here, and say this one is at t equals to 0. All right. This is the wave when it was at t equals to 0. If I wanted to plot a graph of displacement time, sorry, displacement distance, not time, displacement distance for the current wave, it looks like this right now. All right. But then what happens if I let time run? This one is the displacement distance at t equals to 0. If let's just say I let time run, the wave will now move to this new position here. Okay, maybe I let time run even more. Okay, so let's just say I let time run until say 5 seconds. So my displacement distance graph will now look a bit different. All right, so this is now the new displacement distance graph. It now looks like this. All right, it's still the displacement of all these individual particles here, but at different timing. All right, so I could say that this one was the displacement of particle A, B, C, D, E, F, G, and I. The same could also be said for this. This one would be A, B, C, D, E, F, G, and H. Okay, they are all just different displacements of the particle right now at a different timing. Say this one now is at t equals to 5 seconds. All right, so this is the main difference between a displacement time and a displacement distance graph. If you are talking about displacement time, I could say that I single out particle C. When I want to plot a graph of its displacement time, it also looks like this. But here I'm only considering the displacement of a single particle with respect to time. But when it comes to displacement distance, you're considering the displacement of a range of particles in a given distance at a particular time. Okay, so that's one of the main differences between displacement time and displacement distance. All right. Now, if given any displacement time and displacement distance graph, there are certain terms there that you should know how to deduce. All right. The first term is displacement. So as I mentioned just now earlier in passing, I mentioned that displacement is the distance of a particle from equilibrium position in a specific direction. If you learn kinematics already, you would have learned displacement as distance from a reference point in a specific direction. So for the wave chapter, you're actually modifying the definition for displacement a little. You just change the reference point to equilibrium position. Okay, and then you have another term called amplitude. Amplitude is just simply the maximum displacement of a particle from its equilibrium position. All right. And then period T is the time taken for one complete oscillation. Frequency F is the number of oscillations per unit time. How these two are related to each other is by this, where we tell you that frequency is equals to 1 over period. All right. And then wave speed V is the distance traveled by a wave crest per unit time. Wavelength lambda is the shortest distance between 2 points that are in phase. Okay, the part where we say in phase, this one, if you don't really get it now, just don't worry about it. Wavelength can also be defined as two other things. I mean, it can be worded differently, where we tell you wavelength is shortest distance between adjacent. Sorry, let me write it better for you. Wavelength can be defined also as the shortest distance between adjacent crests. Okay, right. Wavelength can also be defined as the shortest distance between adjacent. Sorry, wait. The wording here is a bit odd. You can just write it as this. Sorry, the shortest distance between crests or wavefronts. Okay, it can also be distance between adjacent crests or wavefronts. Okay, notice that there's some slight difference here. Here we say shortest distance between crests. Here we say distance between adjacent crests or wavefronts. They actually mean the same thing. When you want to find out what's the wavelength of a wave, you will normally tend to look at it from a displacement distance graph. Okay, so wavelength is the shortest distance between crests or the distance between adjacent crests, which on this graph is these 2 points here. All right, now if I try to extrapolate this graph, you get something like this. All right, you see, there's a reason why we put the term shortest distance or adjacent crest. If let's just say I say wavelength is just distance between crests, this one is very vague because you see in a wave you have many crests. This is the first, second, third, and then this one is the fourth. So when you say distance between crests, it could mean this one, it could mean this one, or it could also mean this one. So when you say distance between crests, this one is not the proper definition of wavelength. You need to have a more precise term inside where you say specifically either shortest distance between crests, which will automatically imply this already because this is the shortest possible, or you just say distance between adjacent crests, which would again imply is this. Okay, so just be careful of that. All right, so that is wavelength. So your graphs or displacement time and displacement distance, you can actually find out all these properties. All right, so displacement you can see from both graphs. Amplitude you can also see from both graphs. Period can only be found from a displacement time graph. Okay, because you need to look at the x-axis value. Only the period, only the displacement time graph has the unit of time. So you can only deduce period from a displacement time graph. All right. Then it's from the period that you can get your frequency. So just now I told you, if you know the period, you can get your frequency as 1 over the period. Right? Okay, wave speed you cannot deduce directly from the graph. You have to calculate it out. In IGCSE or SPM, you will have learned that V is equals to F lambda. All right. If over here you manage to find frequency, you can put it inside here. And then for displacement distance graph, you can find wavelength. You put it inside, you will be able to find your speed. All right. So that one is okay. So just now wavelength, I told you already, you can only deduce it from your displacement distance graph. In layman terms, it's just simply the distance between adjacent crests or shortest distance between crests. All right. Okay, then another thing I should go through here with you before I go through any questions is this one. Now, just now when I was explaining to you how they plot the displacement distance graph, I was referring to the example of a transverse wave. Wait, let me show you again. Just now when I explained to you how we get the displacement distance graph, I was using the example of a transverse progressive wave. Okay. Now for longitudinal wave, when you want to get the displacement distance graph, the shape would also be the same. But when you look at how a longitudinal wave behaves, and you compare with a transverse wave, it's a bit hard to visualize how they get the displacement distance graph, right? If just now I was using the transverse wave example and I show you how to get the displacement distance graph, that one is quite forward to see how they get that graph. But if you're talking about a longitudinal wave, and then you're asked to visualize how they get the displacement distance graph, this one may seem a bit tricky, all right? So this one is what I need to explain to you right now in the current page of your notes under page 3, all right? Okay, so when you're talking about displacement distance graph for longitudinal waves such as sound wave, longitudinal waves like sound usually have what we call as compressions and refractions instead of crests and troughs for transverse wave. If you're wondering what is a crest and trough, if I have a wave like this is what we call a crest. This is what we call a trough, okay? This is normally what we use for transverse wave. But for longitudinal waves, we have something called compressions and refractions, especially for sound waves, all right? In your exam questions nowadays, you will often be asked to identify which points are compressions and refractions, okay? So this diagram that is shown here is actually a snapshot of a longitudinal wave, all right? They froze it in time at a particular time, and this is what you see right now. There are certain points that will be known as compressions, which is these points here. And then similarly, there will be some points that are known as refractions, okay? Now, compression term is easy to see. Compression is where you tend to see the particles being squashed together or crowding together, all right? It's a region in the longitudinal wave where the particles are closest together. You tend to see the particles crowding together towards that particular point. Then refraction is actually something like an expansion point. It's similar to an expansion point, all right? Is where all the particles seem to spread out, all right? The particles are actually the furthest apart at these points. The particles are spreading out, all right? So in your exam questions, whenever you're given a displacement distance graph, you will often be asked to identify from some of these indicated points which point is actually compression, which point is actually refraction, just by looking at the displacement distance graph. So to be able to deduce which point is actually your compression or refraction, you need to first understand how they produce the displacement distance graph in the first place, all right? So let's just say, for example, I make use of a longitudinal sound wave as my example right now. Let me clear off the diagram. All right. So let's just say right now I make use of a longitudinal sound wave. All right. This entire line here represents the air particles. This represents the undisturbed air particles before a sound wave travels through it, all right? All these air particles are in their equilibrium position, okay? The undisturbed is referring to the equilibrium positions. So let's just say right now, a sound wave passes through, okay? It passes through the air. And then all these air particles right now are oscillating as the sound wave travels through. So recall that for a longitudinal wave, the particles will tend to oscillate parallel to the direction of wave travel. So let's just say, for example, right now, I have a wave, I have a sound wave that goes towards the right, right? This is my sound wave going towards the right. As the sound wave travels through, all the particles right now have displaced from their original equilibrium position. Okay, so this is where you can get your displacement distance graph. Recall that just now I mentioned to you, when you want to plot the displacement distance graph, you normally do not consider a single particle. Instead, you consider a number of particles over a given distance. So let's just say right now, the distance that you're considering is here. Okay. And then after that, I mentioned that when you plot a displacement distance graph, you're actually plotting the displacement of all those individual particles over a given distance at a certain time only. So let's just say that right now, these are the displacement of the particles at a certain time t. T maybe 1 second, all right? So right now, you want to plot the displacement of all these particles right now at this given time over this given distance. So how do they plot the displacement time graph? Recall that I told you that the first row here represents the undisturbed position. They are at the equilibrium. So you see, if I look at the first particle over here, the equilibrium is here. This particle was before the wave passed through. This particle is after the wave passed through. Notice that it did not displace at all. So this one, the displacement is 0. But then if I go to the second particle, the equilibrium is this line here. Before it got displaced, it was here. After it got displaced, it's now here. Your displacement is actually this much. All right. And also recall that we mentioned to you before that displacement is a vector. So vector has direction or has positive, negative. So let's just say, for example, right now, going towards the right is considered positive displacement. All right. So for the first particle that you have here, it has now displaced to this position and is going towards the right. So it's considered to be positive displacement. So it is represented by this point here. If you go to the third point, this one, again, the equilibrium is over here. Before displacement, your particle is here. After displacement, your particle is now here. So your displacement is this much. Okay, it's still towards the right, so it's considered to be positive displacement. But when you compare this displacement with the previous displacement, this one is larger. It seems to be displaced even more. So when you want to plot your displacement, the displacement for this particular particle at this distance, it is over here. Okay, so you get this. So you repeat the analysis again for the third one, for the third particle. Again, this is your equilibrium position. Once it has been displaced, it is here. Your displacement is right over here. Again, it's towards the right, so it's positive. But you notice that this one is not as large as the previous displacement. So it will just be up to here. Okay, so this one is this. All right. Now, then I move on to the last one. Let's just say I pick a random point. Maybe I pick this one. Okay, I pick this one. Okay, so if I pick this particular point here, maybe I use a different color. I use blue or maybe pink. All right. Say, for example, I pick this particle here, the equilibrium I know is over here. Okay. Before it's displaced, it was over here, but after it's being displaced, it's now over here. My displacement from equilibrium is this one. But notice that the direction of your displacement is now different compared to the first portion. If going towards the right is positive, going towards the left is going to be negative. So this one here is going to be negative displacement. All right. And by how much? Is by this much. So your displacement for this will be negative at this point. Okay, at this point here. All right. You can repeat the analysis for the remaining points. You will see that they give you this. All right. So this is how you plot your displacement distance graph for a longitudinal wave. All right. They look at it in this manner. All right. So over here, what I'll say is that you have positive displacement. Over here, you have negative displacement. All right. Okay, so this is how we plot your displacement distance graph. So far, so good with that. So now, okay, now it's from here that we then deduce out where is our points of compression and where is our points of refraction. So I'm going to clear off all the things that I've written here. You can look at the video recording later if you need to copy anything. So let me just clear off everything here. Now, once you have your displacement distance graph plotted out, you will be asked to identify a lot of times where is your point of compression, where is your point of refraction. Okay, so your point of compression is this point here. Maybe I don't use a dot. Okay, your point of compression is this point. It's here. Your point of refraction is this point here. Okay, now specifically, I just want to single out these two lines. I just made an example of these 2 points. How do I know that this point is going to be a compression in the first place, right? Now, if you want to see whether this point is going to be a compression, what you do is that you look at the displacement on either side of that point. You see, if I look at this point right now, I notice that over here is positive displacement. Just now I wrote here, this one is positive, this one is negative, right? So positive displacement, all your particles are going towards the right. Then you look at the other side. This one is negative displacement. All your particles are going towards the left. So you try to visualize, if you have a particle here, all the particles on your left right now are going towards the right. And then on the right side of your particle, all your particles are moving towards the left. So you see, you get the impression that all the particles are actually crowding together. You know, let me just write it here. Here, over here, you see that the particles are crowding together. Specifically, if you make this you consider this point, you look at this side, all the particles are having positive displacement, meaning to say they're all moving towards the right. And then you look at the right side here, all your particles are having negative displacement, meaning to say all of them are moving towards the left. You're getting the impression that they're all crowding together. So this point here is going to be your compression point. All right. Now you can do the similar analysis for this point too, the refraction point. You will also see a similar logic. So for this part here, when I want to see whether it's compression or refraction, I will still look at the displacement of the particles on either side of that point. So here I already mentioned that it's negative displacement. All the particles are moving towards the left. All right. What about the right side of that particle? The right side of that particle, you will notice again, it is, sorry, maybe I use a different color. You will notice again that this one is positive displacement. Maybe I use black. Okay. You will notice that this is positive displacement where all the particles are moving towards the right. So now you see, okay, this is my particle over here. All right. Maybe I shouldn't use black. It's obscuring it. This particle, this point here is this particle here. So now I look at both sides of the particle. On the left-hand side, negative displacement, all the particles are moving towards the left. On the right-hand side, I have positive displacement, all the particles are moving towards the right. So you see, the particles are spreading out. When you look at this one, the particles are spreading out. So therefore, this one will be a refraction point. Okay, so that is how you would deduce whether you're going to have compression or refraction from a displacement distance graph. You have to look at the displacement direction, whether it's positive and negative, whether it's going towards the right or left, and then from there, deduce whether they are crowding together or spreading out. If they're crowding together, they are compression. If they're spreading out, they are refraction. Okay, so that one should be for this. Okay, so the concept part, I think this one will cover enough to do some questions. Right, so I think I'll just move on to the past years. All right. Do you need to have a short break, or can I just move on to the past years?
I think you can just move on to the past years, yeah.
All right, okay, so let's just move on to the past years then. Okay, so if we move on to the past years, okay, wait, let me just move on to the past year. Okay, so moving on to the past years, let me clear off everything. Okay, one of the first things we can do is probabilities. We know page 26, question 24. Page 27, question 22. Okay, right, let's just go through some selected questions. Okay, have a look at page 27 of the worksheet, question 22. All right. Now you have a transverse wave that travels along a rope. The graph shows the variation with display of the displacement of the particles in the rope along it, with distance along it at a particular instant. This is the, when you see the word particular instance, is actually referring to as at a certain time. That's all. Okay. So you're plotting the displacement of all the particles along the rope at a certain time. All right, this is what you get. So they're asking you right now, at which distance along the ropes do the particles have maximum outward velocity? All right. So just now, one of the first things that I mentioned to you was that particles at equilibrium have maximum velocity or speed either up or either upwards or downwards, right? They have maximum velocity either upwards or downwards. Okay, so right now you should be looking at the equilibrium positions, because those positions is where your speed is going to be max. So you could be considering this one, or this one. All right, but how do I know which one is going to have maximum upward velocity? All right, now just now, if you refer back to the transverse wave, this is how a transverse progressive wave looks like. So let's just say I freeze it right now. This one would be essentially my displacement distance graph. Okay, so say for example, now when I freeze it, this one here is the displacement of all those particles at t equals to 0. So if I tell you this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this is the displacement of all those particles at say time t equals to 0 right now. Okay. Now what happens when I let time run and time becomes t equals to 1 second right now? So when time starts to run, because this is a progressive wave, the wave profile will tend to move from one end to another end. So the red colored section that I highlighted now is the wave profile at t equals to 0. If I let time run, the wave profile will become something like this instead, indicated by this blue colored highlighted section that I have. All right, this is now the new wave profile. All right, so it's from here that you can start to deduce what is the subsequent direction of your particles. All right, so maybe I extend this thing a little. All right, so previously, if I just look at particle A, when t was 0, it was here. But now when t is equals to 1, it is now here. You can see that your particle has actually moved downwards. And then if I look at particle B, before this it was here at t equals to 0, and then now at t equals to 1, it is here. It has moved downwards. Okay, and then if I make another separate example, let's just say particle A, B, C, D, E, and F. Particle F at t equals to 0, it was here. At t equals to 1 second, it is now here. So this particle has actually moved upwards. All right. So when you want to see how a particle behaves once the wave starts to move, it is generally suggested that you draw a wave profile at the next instance of time, like what I've just done. That way, it will allow you to see where the particle is going next. All right. So applying what I've just mentioned here, if you refer back to that little question that we are looking at, this is the wave profile. Okay. This one, I could say maybe it was at t equals to 0. At the next instant of time, this wave profile could probably be somewhere around here already. Okay, let me just draw it nicely here for you. Okay, this one could be where this one is at t equals to 1 second. This one was t equals to 0. So just now I wrote a little statement here. I mentioned to you that particles at equilibrium have maximum velocity either up or down. So I mentioned it will always be at the equilibrium position. Then I mentioned that it could be this one, or this one, or this one. All right, but how do I know which one should it be? Is it 0.5 where it's maximum outward velocity? Is it 1.5 where it's maximum outward velocity, or is it 2.5? So the way to see whether it's going to be having an outwards velocity, you just draw a wave profile at the next instant of time. All right. So you notice that at 0.5 position, this particle at 1 second, it will go up. And then at the 1.5 position, in the next 1 second, it will go down. And then at the 2.5 position, 2.5 meter position, this particle will go up at the next instant of time. All right. So the points where you have maximum outwards velocity would actually be this point here, as well as this point here. Okay, at the 0.5 and the 2.5. These two have max upwards velocity. But the ones over here, this one would have maximum downwards velocity. Okay, so you want the maximum outward velocity. The answer is A. Okay, 2.5 is not inside the answer choice, so you can't pick anything. All right, but here when you look at the graph, you should know that it's actually 0.5 and 2.5. But we can only have one correct answer here, so this is only 0.5. 2.5 is not inside the answer choice. Okay, so just now I wrote here particles at equilibrium position at maximum velocity, either up and down. Then after that, I think I probably should mention this. To determine the direction of motion of the particles, draw the wave profile a short instance of time later. Okay, so when you want to determine the direction of the motion of the particles, just draw a wave profile a short instance of time later, like the ones that I've just drawn. Okay, right. Okay, so this one is okay. Then I move on to the next question. I'll be jumping around, okay, according to the questions that are suitable to what I've just taught. Okay, the next question probably would be, yeah, 32, page 32. Okay, this one is a continuation of what we just done. Just have a look at page 32. Again, it's question 22. So I'll just clear off everything here. All right. Okay, so when a sound travels through air, the air particles vibrate. The graph of displacement against time for a single air particle is shown. Which graph best shows how the kinetic energy of the air particle varies with time? So this is again where you need to make use of this knowledge here. Just now I mentioned the particles, I'm actually rewriting what I just wrote. Particles of equilibrium, sorry, particles at equilibrium position have max velocity. Okay, so I know that particles at equilibrium position have max velocity. Right now, what the question wants is for you to show how the kinetic energy of the air particle varies with time. If given a displacement time graph that looks like this, how would it look like? Okay, so since they're talking about kinetic energy, you see, kinetic energy has a close relation with your speed or your velocity. So you know that Ke is equals to half mv squared, right? So Ke is max at equilibrium position. Okay. So just erase off what I just wrote for the previous questions. Okay. So what you do know is that particles at equilibrium position always have max velocity, and then K is equals to half mv squared. So since the velocity is max at equilibrium, Therefore, KE is max at equilibrium position. Okay, that one you know. All right. And then another thing that you need to know is that KE is a scalar. It has no negative values. Okay. It's only when you're talking about vectors where you have a direction that you have positive and negative to take into account. But since energy in general is a scalar that includes KE, it does not have any negative values. All right. So that's why you see here in your graph, there's no such thing as negative KE. It is a scalar, so it has no negative values. It's only going to be positive. All right. So based on these two knowledge that you have, you can now see that these points where you have equilibrium is where your KE is max. Okay. So these points here is where your V is max. Therefore, KE is max. So if I try to plot it out, it will be like this here. If I try to plot KE versus time graph, this is where my KE will be max. Okay. And then after that, I also mentioned something to you, all right, before. Particles at amplitude position have zero velocity. Okay, so therefore KE is zero at amplitude. Okay, so now at the amplitude positions, my KE will be zero. That one will be indicated by these points here. I think I use black color. See, these points in triangle is where V is zero. Therefore, KE is zero. Okay, so if I try to plot the KE point, the KE being zero, it will be here, 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 and here. Okay, so now I try to join those lines together. I get something like this. Okay, I'm supposed to get a shape that looks like this. All right, so the correct answer for this would actually be D. Okay, right, if you look carefully, this part here is T, right? One period. Okay, notice that in one period you have two bumps. You have these two bumps here. 1, 2. The two bumps upwards. All right. So the only one that shows you a shape that looks like this that has two bumps within a period is D. Okay. Right. So just look at the relative positions now, simply put. Just look at the amplitudes. Amplitude being zero. Sorry, just look at the amplitude position. Amplitude position, velocity is zero, therefore KE is zero. Though. So that one is represented here, here, and here. Okay. And then at the equilibrium position, that is where your velocity is max. That's where you have maximum KE. So that one will be here and here. Okay. That's how you get those two bumps. All right. So this is okay. Okay, so that one is one way of looking at it. Okay, then after that, I move on to some other question. So I'll just clear off everything that I have here. And then we move to page 51. Let me have a look at page 51 first. 51. Oh, okay. Page 51, question 22 also. Okay. Have a look at page 51, question 22 also. All right. Okay, over here they tell you the variation with distance x of the displacement y of a transverse wave on a rope is shown at time t equals to 0. The wave has a frequency of 0.5 Hertz. The point x on the rope is marked. The diagram shows the original position of x and 4 new positions. What's the position of x at time t equals to 1 second? So here you read the question. They say it's a transverse wave on a rope. It's a displacement distance graph. All right. So they tell you right now the wave has a frequency of 0.5 Hertz. A point x on the rope is marked, which is this one. The diagram shows the original position x and 4 new positions. 4 new possible positions, either A, B, C, and D. All right. What's the position at time t equals to 1 second? Okay. So this is a displacement distance graph. What you see here is the displacement of all the particles at t equals to 0. Right now, they want you to look at particle x. What is the position of the particle x when t is equals to 1 second instead? Okay, now for this one, you don't really need to draw a wave profile. Okay, the question before this, I drew for you a wave profile, a short instant of time later, in order for you to see how the particle moves. All right. Now, right now, for this one, you need to approach it differently. Let me just use back the same diagram, same thing as before, same. Okay, I use back the same animation. Okay, so let me just share it with you. Okay, so okay, so right now I show you again that little animation that I've been using since the beginning of this lesson. Okay, so that wave profile that you just saw in your question looks like this right now. Particle x is here. All right, they told you particle x is this point here. Okay, so they want you to determine the position of this particle x at time t equals to 1. So just now I mentioned to you, this one will be where t is equals to 1 second, right? Sorry, this one is t equals to 0. Sorry. This is where t is equals to 0. You want to find out at t equals to 1 second. Okay. Now, one thing that I did not really mention just now to you was this. Just now I mentioned to you that when a transverse wave travels, when a wave travels through something, the particles will tend to oscillate about the equilibrium position. So in the case of a transverse wave, what you do know is that the particles will tend to only oscillate up and down. Okay, they will only oscillate up and down. Okay, now all these particles, when they oscillate up and down, they would have a same period. What do I mean by that is this. You see, for let's just say I label particle A for you, you will see that particle A just goes up, down, and then up. And then if I talk about particle B, you're seeing the same thing. It will just go up, down, and then up. They're oscillating, right? So particle C also same thing. it will just go up, down, and then up. Okay, they're all oscillating. So they're all oscillating, they have a certain period. So all these particles here actually have same period. All right. It doesn't matter which particle I talk about. I could be talking about particle A, B, C, D, E, F, or G. They all will oscillate up and down and have the same period. So the question just now mentioned that you have a frequency of 0.5 hertz. Okay. Just now the question mentioned that your frequency is 0.5 hertz. Let me just write it over here. The frequency is 0.5 hertz. You want to find out what is the same, what's the period? Period is 1 over f. So 1 over 0.5. It will give you, 1 divided by 0.5. It will give you 2 seconds. All right. So let's just say right now your particle X is over here. All right. I will say it's particle D right now. All right. Okay, now maybe I don't use particle D. I specifically label this as X now. Okay, this is particle X. All right. So when T is equals to 0, wait on, let me just post it at the correct timing for you. Okay. So when T was equals to 0, this particle X is here, as indicated in your diagram. Okay. So it will oscillate with a period of 2 seconds. So when it oscillates with a period of 2 seconds, if it wants to make one complete oscillation, you will see that it needs to go from this position at the top, go all the way down, and then go back all the way up. This one is 1 period. Okay, but you also notice that this one can actually be separated, this entire motion here, from the top, going all the way down and then going back up to complete one oscillation, thereby giving you 1 period. This one can be divided into 4 sections, right? You can see that this one can be divided into, okay, now this is getting a bit messy. Let me just rub off certain stuff. Okay. You can see that this one can be divided into 4 sections. One motion here like this, one motion here like this, and one motion here like this, and like this. This all add together gives you 2 seconds. So similarly, you can say that each of these sequence here can be 0.5 seconds. Because you see what you're doing here is that if you take 2 divided by 4, you're going to get 0.5 seconds, right? Basically, in one oscillation, you're dividing it into 4 distinct sections. So this one here is 0.5. This one is 0.5. This is 0.5 and 0.5. So you're getting back 2 seconds for one complete oscillation. So right now, what the question wants here is this. What is the position of X at time t equals to 1 second? So if I, wait, just now I shared something, right? Okay, whatever I just wrote there actually has been deleted because I screenshot something else. Yeah. Okay, so let me just go back to here, all right, to the original question. So right now they want you to find out what is the position at t equals to 1 second. So just now I mentioned to you, period is 1 over f is 1 over 0.5 is equals to 2 seconds. So this one here at particle x, for particle x, it can be divided into 4 distinct motion that gives you one oscillation. One going down like this, one going down like this, another going up, and going up, right? So this one will be 0 0.5, 0 0.5, 0 0.5, and 0 0.5. So if they want at t equals to 1 second, you will be going here and here, like this. So your answer for this question, what's the position of particle x? It will be at B. Okay. This one you don't draw wave profile to find the answer. This one you try to visualize what happens to the particle itself as it tries to go one whole full cycle of oscillation. All right. So here the answer is just B. Okay. So C and D cannot be the answer because particles do not get transferred with the wave. Do not get transferred along as the wave moves. Okay. All right. C and D you cannot choose because the particle itself doesn't get transferred to here. Just now, one of the first things that I mentioned to you at the beginning is that the particles will only oscillate about their equilibrium position. They do not get transferred from one end to another along with the wave profile. Okay, so it's just going to oscillate up and down, up and down. Your only possible answer choices is either just A or B. Okay, but then from there, which one is it? You just look at how it oscillates and relate it to the period of 2 seconds. Okay, so that one should be okay. The answer is B. So the next one that I should probably look at is page 57. No, this one is 51. Okay, so let me go to page 55. No, 55 is something that I've just done. Wait now, 32, 27. Okay, page 55, question 23. This one is a repetition of what I just done. This one you can have a look at it later. All right, you can just have a look at this one later. It's actually the same question, so this one I will just skip. All right, it's the same question as the one that I've just done earlier. I want you to look at page 57 instead. Okay, so 55, you can do this as your homework later. Okay, 57. Okay, 57 is good. Have a look at page 57. Okay. Page 57, question 24. All right, now you have a wave that moves along the surface of a water. The diagram shows you the variation of displacement as with distance along the wave at time t equals to 0. Okay, so this is a displacement distance graph. Okay, it's a displacement distance graph when t is equals to 0. All right. So right now they're asking you, which graph best shows the variation with time of the displacement of point P on the wave? Okay, so this one is like something a bit different. Okay, let me just zoom it out. Okay. All right, so you can see everything. Okay, right. So they mentioned to you, this is page 57. They mentioned to you that this one is a displacement distance graph. Okay, displacement distance graph, this and this. They want you to look at point P and then ask you to plot a graph of displacement time. All right. Right now, what you have here is a displacement distance graph. Basically, what they're asking you right now is from this displacement distance graph, for this particle P here, plot the displacement time graph for this particle. All right. So this one would combine a lot of the stuff that I just mentioned to you earlier. Okay. Now, if you look at this particle P, maybe I just draw another one here. Some things to ponder about later on. Okay. So this is the particle P. Let me just draw it here for you. Particle P is here. Okay. Now, particle P is this one. Maybe I should draw two just to highlight. Okay. I had two of the same thing right now. Okay, this is particle P and particle P. So just now I mentioned to you, when you're talking about a transverse wave, the particles will just oscillate up and down. Okay, so right now, specifically for particle P, you do know that they're just going to oscillate up and down. Okay, but right now the issue is, how is it going to start its motion first? Is it going to go up first and then go back to its position to make one oscillation like this? Or is it going to start downwards first and then go back up and then go back to its original position? How do I know which one is which? What you do know is that this particle P will oscillate up and down. Okay, you're trying to plot a displacement time graph right now for point P, for particle P. You do know that it's just going to oscillate up and down. But how do you know between this one and this one, which one is the correct one? Is it going to be going upwards first before going down? Or is it going to be going downwards first before going back up to complete one oscillation? So this one, to know which of this is going to be the correct one, you will need to plot the wave profile a short instant of time later. Okay, so this one here, as I mentioned to you, is probably t equals to 0. So if I want to find out how the particle moves a short instant of time later, what you would need to do is you plot the wave profile shifted a little, maybe something like this. Okay, just plot it slightly away. This one could be the wave profile at 1 second later. Okay, now once you plot the wave profile shifted a bit towards the right, you will then be able to see very clearly that particle P is actually trying to move upwards. Okay, so you then know that this one should be the correct one. This one is out. Okay, so what I'll just say here is to determine whether P moves up or down first, draw a wave profile. Draw a wave profile. Draw a wave profile. A short instant of time later. Okay, so by drawing the wave profile a short instant of time later, you can see that the particle is going to move up. All right. Then after that, also notice one thing. Actually, this one should be point number 2. Okay. Now you see, when you look at the answer choices A, B, C, and D, Notice that B is where your position is 0. This one is not correct, because you see at t equals to 0, P is already displaced from equilibrium. Okay, it's already displaced from equilibrium. Okay, therefore cannot be B, right? Because you see at t equals to 0, my particle P has already been displaced from equilibrium position. It's already, this is the equilibrium. It's already gone up to here. Okay, so I should have a displacement already going upwards. I should have a displacement upwards already. So it cannot be B. It cannot be C also, because it's already displaced upwards. Okay, so cannot be B and C. All right. So you only left with either A or D. Okay, both of them are starting at the correct displacement, but now here is where you start to choose now whether should it be going out or whether should it be going down. So just now I explained to you, you just draw a wave profile short instant of time later to see whether it's going up first or going down first. You already determine it is this. Okay, so it's going to go up, then go down to go back to its original position to complete one oscillation. The one that shows that is actually going to be this. So your answer is actually going to be D. It cannot be A because you see it's going down and then going up. This one you see is going up and then going down, going up again. All right. So it's not A, it's not B, it's not C. The answer is actually D. Okay. So good. All right. Okay, so let me just see whether there's something else from here.
Wait, oh, sorry. Can I just ask a question real quick?
Yeah, sure.
In terms of drawing the wave profile, like
Yep.
a short distance later, right? Like how short is short? Meaning, is it would it change would it change the direction if let's say I do it a bit too far away from?
Yeah, if you draw it a bit too far, you will change it a lot. Wait, let me just clear up the diagram here. Okay, you're asking this one, right? If
Yeah.
you draw it too far, okay you should not be drawing it too far away. Just now when I drew it a short distance away, something like this. This one, it will clearly show you that your diagram, your particle is moving up. But let's just say you draw it too far away, like maybe here like this, I draw it in blue. Maybe you draw it too far away, maybe you move like this. Okay, maybe you move like this. This one is telling you it's going down, right? So this one is too far already. Okay, you need to draw it a short distance, a very short distance away, like this. This one should be the correct one. Okay, if you draw it too far, like the blue colored line here, it's going to tell you something else. Okay, it's actually telling you your particle P is going down, but this one is too far. What we normally tend to do is we draw it a very short distance away, like this pink colored line here. Okay, when you draw a pink colored line here, this one will tell you it's going up. Okay, it will eventually go back down, but that one is when a lot of time has passed. Okay.
I see. Okay, thank you.
Right.
So I just have to try to like draw
Don't
it
draw
as
too
close
far.
as possible lah.
Yeah, just draw it a bit away, then you'll be able to see. If you draw it too far like this, like the blue color line, this is already wrong. Okay, you've already gone past already. All right.
Okay, got it. Thank you.
All right, no worries.